I'm going to talk to you today about multiple effect distillation and CSP plus desalination. We already heard a talk about this morning, giving us a lot of excellent financial information about the process. I will refrain to talk about economics, rather focus on the technological aspects and see the future of this technology and what it is, if it has some. Obviously, the problem is here, and it's very pertinent. We have currently about 3 billion people suffering from insecure supply of fresh water. And if we look at the water stress index, which is a ratio of water use to water availability, and we see this in the future, we see that it affects almost everyone on the planet. And in fact, in view of climate change, we have, especially for the region, we have projections that precipitation will decrease, exacerbating this problem itself. Of course, desalination is a solution to the freshwater supply, as about 97.6% of the Earth's water is in a saltwater form. Of course, removing this salt is the objective of the study, and it is an energy-intensive process. Just indicatively, in Cyprus, we spent, here I say 4%, but it's in fact a little bit higher than that, of the annual energy produced for desalination purposes. And the reason this number is so high, it's not only a problem of Cyprus, it's a global problem, is because of the thermodynamics of the separation process. So if we have various solutions of seawater, we can calculate the minimum amount of energy required to remove the salt for a particular recovery ratio, so the amount of fresh water we recover from a fixed volume of seawater. So as we increase the salinity of the mixture, this energy is also going to increase, and we can find thermodynamically what this limit is for particular concentrations using purely work. If, however, we use heat as a source, these numbers change. It's about a factor of magnitude larger. And of course, as we increase the temperature at which we have this heat source, because of the Carnot efficiency, we will drop the energy requirements. But at temperature levels where we're talking about these processes at 50 to 100 degrees, we still have fairly high energy requirements of about 5 to 10 kilowatt hours per cubic meter of water production. Of course, we can look to the sun to get this energy, and this is the objective of this talk. Obviously, there's a very good correlation between regions that have high solar potential and lack of fresh water. That's why we think that this solution is a very good one. In fact, it's something that we propose at the Cyprus Institute through the cogeneration of electricity and desalinated seawater by taking all the heat available from a CSP system, storing it, and then in parallel producing both power and desalinated water. And in fact, it's the optimal coupling of these two cycles that gives the advantage for the CSP plus desalination solution. The thermal desalination process that we are talking about is the multiple effect distillation. For those of you who are not aware of the process, you have a heat exchanger into which steam is introduced and seawater. As the steam condenses, heat is transferred to the seawater, causing it to evaporate, and then we use these vapors to drive as the driving force in the next effect and subsequent effect to desalinate another quantity of seawater. And I have some schematics and pictures of our experimental setup. One of the novelties that we have that I'll come to later is the plate heat exchanger, which we'll discuss a little bit later. In fact, we've done several studies to analyze the behavior of the system. The one that I want to focus on is to see how the specific energy requirements decrease as we increase the number of effects of the system, which is in fact the strength of this, or the advantage of this multiple effect distillation technology. We've also come up with some models to predict the behavior of these systems that they match fairly well with the literature process, and we've also focused on the dynamic and transient simulation behavior of the system itself. The reason for doing this is that we're interested in coupling the process, as I said, with the solar-driven process, and when we have a process that is not steady state, then we have to better understand the transient behavior of this nature and see what the time response would be when we drive our desalination process with this transient with this time varying resource. So it's a tool for the plant operator to understand when to divert energy towards desalination or towards the electricity production, and understand the product that he will get based on the transient nature of the resource. Of course, we can look at the energy flow in a typical solar plant. We have the energy coming in, reaching the light concentration and collection plant, and have some losses there due to cosine effect and other efficiencies. And as we go through the conversion process to electricity, we have various losses throughout the system. In fact, we've done a similar study for our particular setup in the Proteas facility, and identified several locations from where we can have high-grade heat or low-grade heat that we can use to drive the process. In this particular study, we identify the conventional location to draw power, which is after the turbine. But as we've already discussed, this comes with a penalty to the turbine and to the electricity production. However, it's been briefly touched upon in the discussion that we can design the two cycles together and design the field together. So in our particular case, we have also some losses that we can capture from the receiver, and thus converting them from losses to a useful energy that can be produced in the system itself. Other studies have also focused on comparing what and Diego showed almost the exact same schematics. This is one of his studies. So we can compare what a CSP plant that would use the electricity produced in an RO to generate desalination, or a truly coupled CSP and MED plant, how they would behave. So what this study shows is a way to integrate the low temperature desalination process, and what is given in the table is the specific electricity consumption of the RO. It's parametrically done as the specific electricity consumption of RO increases, and as the specific electricity consumption of the MED increases. And the bold numbers indicate the advantage for the MED system. So this is an encouraging result, and it shows that under certain conditions, the coupled CSP plus desalination is favorable. But then it's also instructive to look at what the market is doing. Currently, we have about 100 cubic million million cubic meters of water per day produced. And you can see that it's nearly an exponential growth over the past 40, 50 years. But the current market is dominated by reverse osmosis. And if we also look at projections of where this technology is going in the future, in fact, the RO, which is the light blue lines, also dominate the future expansion. And the reason for this is simple. Over the last 40 years, the specific energy consumption of RO has significantly decreased. With red line is the thermodynamic limit that I showed you in the beginning. So the specific energy consumption of RO has dropped by almost an order of magnitude over the last few years. So this poses the question that Diego already addressed. Is thermal desalination dead? What is the future for thermal desalination? So we don't think so. We think that there's several specific technological applications, locations where we can have an advantage. One of them is the plate heat exchangers. So this is a specific type of heat exchanger as opposed to the shell and tube heat exchanger that's traditionally used in these applications. The nice advantage about these heat exchangers is that they are compact. They have higher heat transfer coefficients. In fact, that's what's plotted here is the variation of the heat transfer coefficient as a function of flow rate and temperature. And on the left is for a plate heat exchanger, and on the right for a shell and tube heat exchanger. So of course there's a large variation for the plate heat exchanger, but if we have a correctly designed heat exchanger, we can achieve maybe 2 to 3 times larger heat transfer coefficients, which means half to a third the size of the heat exchanger, and also the equivalent cost reduction in capital. We can also think about using other inexpensive materials. The previous heat exchangers had that we use here have titanium as the heat transfer surface because of its corrosion resistant properties to salt. However, we can think about novel polymer materials to do this desalination. And I show you some examples from the literature about what people are coming up with to use these examples. We can also consider novel manufacturing techniques like 3D printing to optimize both the heat transfer area and the pressure drop that we have in these exchangers to ultimately decrease the cost of this technology for the future. Finally, we need to focus the cogeneration of the coupling of CSP and desalination and use all the available energy that we have to drive the thermal desalination process. In fact, we can not only use the low-grade heat after the turbine, but we can also harness other losses at higher temperature to be able to drive, let's say, a coupled thermal vapor compression and multiple effect distillation system, which leads to higher yields, so more water production from the system and equivalently less cost. Also, we need to focus the use of these systems in areas where they have the advantage over the reverse osmosis. For example, focusing on higher brine concentrations and more water recovery to reduce the pumping cost that we have. And this is again something that can be achieved through the use of the new materials, the polymer materials, that will also reduce the fouling effects and the limitations that we have with the current technologies. Finally, zero liquid discharge is a very promising aspect, although it is very energy intensive as a process. We can think about, again, using the heat that we have from the solar system to aid this. So with that, I would like to thank you for your attention and conclude my talk.